All right, cool. Now I'm recording. Um, awesome. Other questions? All right, so one final reminder, tomorrow is your midterm exam, 11 o'clock. Hop into Zoom for it so I can share corrections and clarifications, and try not to miss it and not to be late. And hopefully, if we get snow, hopefully that doesn't impact taking the exam. But we'll play it by ear. All right, let's talk about efficiency of tree operations. So we've been talking about binary search trees for a few days now, and we already spent a while developing linked lists. And the idea of linked lists was to improve on the efficiency of arrays. And the downside to linked lists was we couldn't do an efficient search because we always had to start at the first node and just follow it until we found the node we were looking for. And so we wanted to be able to play high-low on linked lists, and so we introduced a pair of pointers to let us go to the middle of sublists, and that turned into a binary tree. And the hope was that the binary tree would restore this log n behavior that we've been seeing with sorted arrays, right? Restore the ability to play high-low. So let's look at what goes on in a binary search tree. So here's a sample of a tree. This has 15 nodes. And we know the basic approach for searching for something in this tree, right? We start with the root. If that's what we're looking for, we're done. Otherwise, we move either left or right, depending on what we're looking for and how it compares to the root. And once we've moved to one of these nodes, we do the same thing. We see if that's what we're looking for, and if it's not, we'll move to either the left or the right. And so now there's 4 different places we could end up, and again, we see if that's what we're looking for, and if not, we'll move to either the left or the right of that node. And then at that point, if we don't find what we're looking for, we can say it's not in the tree. And so even though we have 15 things in our tree, for this particular tree, the most number of comparisons we're going to have to do is 4. Right? For example, suppose we were looking for this piece of data. We would compare our number to the root and move left, compare to this node and move right, compare to this and move right, compare to this, and there's our data. And if the data is not in the tree, we would compare to this, and we wouldn't find it, and we'd see there's no children, and we'd say it's not in the tree. So number of comparisons, worst case, is 4. Now what's the best case? What's the fewest number of comparisons we might need? One, yeah. It's possible that, the thing we're looking for is right there. In which case, one comparison, hey, we're done. So if we end up looking for the root, we're in really good shape. But worst case, which is usually what we're interested in, 4 operations. Well, that's pretty good. With a linked list, 15 nodes if we're looking for the last thing, or we're looking for something that's not in the list, 15 operations. With binary search tree, it's only 4. So that's with 15 nodes. If we had twice as much data, 31 pieces of data stored in here, and this tree was still, you know, nice and fluffy like this, now what's the worst case number of searches, number of comparisons? It's 5. It's gone up by 1. This is why log n is so nice. You can double the amount of data, and to find something you have to do one more operation. Okay, that's characteristic log n. Twice as much data, do one more thing. If we double it again, we do one more thing beyond that. So if I increase my data by 1000x, I'm going to have to do 10 more searches, 10 more comparisons. If I have 1,000,000 times as much data, I have to do 20 extra comparisons. If I have 1,000,000,000,000 times as much data, I have to do 40 little comparisons, and that's it. Right? So this is a really nice way to organize information if you want to be very efficient at working with your data. But this is for a nice looking tree where everything is like filled in and fluffy. 15 pieces of data could be stored in a very different way in a binary search tree. Right? It could be the big pathological tree where all the nodes only have one child and it's basically a linked list masquerading as a tree. And there, how much work do I have to do to look for something? Potentially 15 operations. So this ends up being back to order n instead of order log n. And I didn't say it explicitly, but the number of operations you have to do is basically log n, where you have n nodes. It's log base 2 of n. And you can wave your hands around, you know, an argument that that's the right formula for the number of operations because, you know, it's right for a few levels, and then when you double the number of nodes, you add 1 to the number of searches you have to do. So this is going up by 2 to the n. All right, so this is a tree where we get really nice search behavior. This is a tree where we get really poor search behavior. So let's look at how we can analyze this. In PA3, do I have to process if you just hit enter without a number? If you hit enter without a number, that's an illegal command, so you should give a help message. Alright, so we're going to introduce some terminology here. Let me update some notes here. Is it okay if it does nothing like in a shell? No, it should give you a usage message because that's an illegal command. Or rather, it's not a legal command. So the depth of a node is the number of hops you have to take from the root of the tree to get to that node. So for example, this node right here, if we want to find its depth, start from the root. We go 1, 2, 3 hops. That's got a depth of 3. Yeah, this could be worse than stick.sh, right? So this has a depth of 3. This node right here, start from the root, we have to go 1, 2 hops. This has a depth of 2. What about these really deep nodes? What's the depth of this node right here? Six. Right? Just start at the root. 1, 2, 3, 4, 5, 6. And the way I've drawn this tree, where, you know, things are sort of lined up, everything at this level is going to have a depth of 6. This node also is going to be 1, 2, 3, 4, 5, 6. Doesn't matter if I go to the right or go to the left. Everything at this level is going to have a depth of 2. So depth has kind of a visual interpretation, right? It's how far down the tree you are. But be careful about, you know, what does, you know, is it 2 or is it 3? Well, I count 1, 2, 3 nodes, but the number of hops from the root is 2, which means that these nodes are at a depth of 1, which means the root is at a depth of 0. And that's important. Root has a depth of 0. And if you remember that, then, you know, the rest of this sort of follows intuitively. This is going to be 1 because it's 1 deeper, and 2, 3, 4, 5, 6. Alright, so that's one definition. That's a property of nodes. Let me give you a definition that applies to the whole tree. That's the height. So the height of a tree is just the depth of the deepest node. So look at every node in the tree, see what the depth of each node is. Whatever the largest depth is that you find, that's the height of the tree. So this tree has a height of 6. And again, that's a property of the tree, whereas depth is a property of a node. Yeah, I know, the trees are upside down. It's kind of weird, but that would be kind of interesting if, like, your ceiling was covered with trees. That would be pretty cool. I don't know how you'd water things. Well, you could water from the roots. That would make more sense anyway. Someone must have done that. There must be some break room at Google somewhere that has trees growing out of the ceiling. Yeah. I didn't know people put Christmas trees on the ceiling. That's kind of interesting. Alright, so the height of the tree is the depth of the deepest node. And there's a special case here. So, you know, if you had a tree that contained just a root, what would the height of that tree be? So a tree just containing a root node, what's the height? It's 0 because the deepest node is the root, which has a depth of 0. So the height of this tree is 0. But there's a special case. A null tree has height -1. So a null tree is a tree with no nodes. It's a totally empty tree. Different from a tree that has a root. If it just has a root, the height is 0. If it has no nodes in it at all, then the height is -1. So yeah, what about people who start counting at -1? All right, so we've got a height of trees. So let's say you have 7 pieces of data. Here's one way to store those pieces of information in a tree. And this is a nice tree because the height is pretty small, right? So the height is equal to 2. Here's a different way to store those same 7 pieces of data. It has a height of 3. Right, that's the worst way to store them height-wise, which is a height of 6. So we could have, the same pieces of information stored in these different arrangements, and they would each be a binary search tree, and they would each be something we could traverse and get our data out in the correct order. But the heights are fundamentally different. And here's the punchline about heights, right? The shorter your tree, the less work you have to do to look for something. Since the height is 2, we know we have to do, 1, 2, 3 operations at most. Here the height is 3, we might have to do 1, 2, 3, 4. Here the height is 6, we might have to do 7 operations. Let's see, you could make a tree faster to search if you change which node you consider the first node of the tree. That's probably true. Or if you had multiple roots, if you had 3 roots, the actual root and then a root that goes to the middle of the left and right subtrees, and you could cut your time down. And you could make 7 roots or 15 roots, and you could store all of those roots in the data structure so that the correct root would take you immediately to the thing you're looking for. And what would you store those roots in? You'd store them in a tree. So there's probably something in there. All right, so let's look at this question of differences among trees with the same set of data. So there's a notion of balance, right? Okay, there's an informal notion of fluffiness, right? This tree is nice and fluffy. It's got lots of stuff up here. This tree, there's lots of stuff here, but we could have some things over here, and we don't. And we could have some things over here, and we don't. So the notion of fluffiness is basically filling in the tree from top to bottom, trying to put a lot of stuff at this level before we go down any deeper. And this is the most unfluffy tree. It's really just a stick because, we've got the root's fine, but down here at this level, we only filled in half of it before we went deeper. And at this level, we had enough space for 4 things, we only used 1. And at this level, we could have stored 8 things, and we only have 1. So if we have a tree of height n, how much stuff could we store in it? So a height of 0 we can store one thing. A height of 1 we can store 3. A height of 2 we can store 7. So it's definitely a 2 to the something situation. And I think the way it works out is it's 2 to the quantity h plus 1 minus 1, where h is the height of the tree. So if our tree has height h, we can store it to the h plus 1 minus 1 things in it. You got the essence of it, right? As long as you got a 2 to the something in there, you're probably, got the spirit of it. The nuances of plus 1 minus 1, are insignificant as the number of nodes goes to infinity. So, roughly 2 to the height of the tree, right? Which means that if we have a tree that looks like this, with, a height of, say, 15, we'd like to be storing 2 to the 15 things in there, right? So 32,000 things, instead of just 15 things. So we'd like to measure the degree of fluffiness, okay? And this is called the balance. Because the other way to think about this is, these things, they're kind of the same on the left and the right. Whereas this thing, it's got more stuff over here on the right than it has on the left. So it's lopsided. So our algorithms will do well as long as the tree doesn't get too high, as long as the depth isn't too big on any of the nodes. How big? Well, no bigger than it has to be. Right? If you've got 1 million nodes of data, you can't stuff it all into a tree with a height of 2. That's just not possible. But 1 million nodes, you should be able to put it into a tree with a height around 20. So we have this notion of balance, and let me give you a definition of what it means for a tree to be balanced. And this is going to be a little freaky. So a tree T is balanced if, and there's two possibilities. First possibility is the tree is completely empty. And we will say an empty tree is balanced because there's nothing in there. There's no way we could arrange the stuff in there any better. So kind of by definition, an empty tree is going to be balanced. But there's a more interesting possibility. A tree can be balanced if all three of these are true. So all three of these have to be true for the tree to be balanced. The height of the left and right subtrees have to be close to each other. So any tree that's not empty, right, we can treat the root as having a left and a right child. Those might be empty. But those left and right children are the roots of subtrees themselves. So we can talk about, let's just say T dot left as the left subtree. And we can ask what's the height of that. And we can look at T dot right, and that's another subtree. and we can ask what's the height of that. And we can take the absolute value of those differences, and that absolute value has to be less than or equal to 1. So the first of our 3 requirements are, if you look at the tree as 2 subtrees connected to the root, they have to have similar heights. They can be a little bit off. They can be off by as much as 1. On PA3, if our program does weird stuff when we had very long digits, like add 2 elements to the list or something, do we need to debug that and solve? I'm not going to test it with anything bigger than a 9-digit number, but the nature of your question makes me think that maybe you're doing an scanf instead of an fgets, or you're doing a scanf instead of an fgets, and it's picking up extra stuff the next time around, and that can get you into other problems. So make sure that it handles typos correctly, and make sure it works with negative numbers. Cool. Alright, so 3 things for a tree to be balanced. First, the height of the left and right subtrees have to be close to each other. That's pretty straightforward, right? Alright, the other 2 requirements are where life gets interesting. The second requirement is the left subtree has to be balanced, and the third requirement is that the right subtree has to be balanced. It's like the first rule of Fight Club, right? So this is the definition of a tree being balanced. Left and right subtrees are close to each other in height, but also those left and right subtrees have to be balanced. Now, it may or may not seem strange that in our definition of what it means to be balanced, we're requiring that we check to see if something is balanced. Right? How do you know if you're happy? Well, are you happy? If you're happy, then you're happy. That makes no sense. That doesn't get us anywhere. Right? But that's not exactly what we're doing here. We're not asking inside here if t is balanced. We're asking if something smaller than t is balanced. Are the left and right children balanced? So let's apply this to a problem. Exactly. To understand recursion, you need to understand recursion. And yeah, this does end up working all the way through the tree. Alright, here's our tree. And we want to know, is it balanced? Well, first thing we say, is it null? No. Okay, so we're going to go on to case 2. We're going to look at the height of the left and right subtrees. So let's figure out what the left and right subtrees are. Well, the left subtree is just one node, and the right subtree looks like this. Everybody okay with that? Because we're going to spend about 5 minutes developing this. And if you come back and you don't know why this is the right subtree, then everything is lost. Alright, so here's our tree. This is the left subtree. This is the right subtree. So questions about that? Why is right left again? So this is our tree T. This is the root. If we look at everything to the left of the root, that's all we got. We got one node. That's the left subtree. If we look at everything to the right of the root, that's all we've got. It's a tree like that. Good. All right. So now to know if our tree is balanced, I'm going to put a little asterisk here because this is our main question. So to know if our tree is balanced, we have to look at the height of the left and right subtrees. All right, well, the height of a tree with just a root is 0, and the height of a tree with one node that's one hop from the root is 1. And so the height of these differ by less than or equal to 1. So step 1 is true. So condition 1 is true. All right, so now we need to know, is this left subtree balanced and is the right subtree balanced? And if they are, then this is balanced. Well, let's see if this tree is balanced. So I'm going to push this page onto my stack, and I'm going to make a subroutine call. And I'm going to go down, and I'm going to, call my balance function on t.left. Okay, what's t.left? It's this. So now I have a completely new state of mind where my tree looks like this. And I'm asking, is this balanced? Well, let's see. Is it null? Nope. Okay, well then I need to look at its left and right subtrees. Alright, so the left subtree is null, and the right subtree is null. So the height of this is -1, the height of this is -1. -1 minus -1 is 0, the absolute value of 0. The heights are the same, so they're within 1 of each other. So condition 1 is satisfied. So the next question is this tree balanced? And is this tree balanced? Well, I'm going to have to call my balance function, right? And see if the left and right subtrees are balanced. So I'm going to push this onto my stack. Let me label this, 1. I'm going to push this onto my stack, and I'm going to call my balance function, and I'm calling it with a tree, which is null. And my question is it balanced? Well, let's look at our algorithm. The algorithm says if it's null, then it's balanced. So is this tree null? Yes. And so it is balanced. And I return from my balance function. Where do I return to? The last place that I was. It's a stack structure. So I return to this page we were just on, and I say, hey, yes, this is balanced. All right, one more step to my balance algorithm, see if the right subtree is balanced. Well, the right subtree is null, so I'm going to call my balance function with a null argument, and my algorithm is going to say, hey, the tree is null, it's balanced. So that call is going to return and say, yep, this tree is balanced. All right. My heights are within 1, the left subtree is balanced, the right subtree is balanced. My algorithm says, therefore my tree is balanced. So it says, yes, it's balanced, and this returns to wherever I called this from. Where did I call this from? I called it from my main program where I said, is this tree balanced? And I just answered this question, yes, this tree with one node is balanced. Right, that's what all of this was about. Now we need to know if this tree is balanced. So we're going to call our balance function with the following tree and asked if it's balanced. Is it null? No. So let's look at the left and the right subtrees. The left subtree is this, the right subtree is null. Criteria 1, the height of this is 0, the height of this is -1. Those heights differ by no more than 1, so criteria 1 is satisfied. So now we need to know if these subtrees are balanced. Alright, I'll do this quickly. I'm going to call my balance function with this tree containing just a root. And we've already seen this before, right? We looked at this, we found the left and right children, the heights were close, those were balanced. My function will conclude this is balanced, it's going to come back and say yes. And then I need to know if this empty tree is balanced, and so I'm going to call my balance function with a null tree, and it's going to say yes, it's balanced. And now my balance function, which is trying to determine if this is balanced, is going to say, are the heights close to each other? Yes. Are the left and right subtrees balanced? Yes. Okay. This is balanced. And now this returns to who called it, and who called it my main program, which was trying to determine if this little 2-node tree was balanced, and balance function just said yes. So what are we doing here? We're trying to see if this tree is balanced, and we're using this algorithm. Are the heights close? Yes. Is the left tree balanced? Yes. Is the right tree balanced? Yes. So my function is going to say, yes, this is a balanced tree. And whoever called this will return and say, yes, it's balanced. Okay, that's a crazy amount of work. It's a lot of flipping of pages back and forth, and a lot of talking. But that's how we use that recursive notion of balance. So in your program, would have two functions, balance right, balance left, that you would call as you work through the tree to check if each branch is balanced. Sort of. Let's take a look at a function for doing this. All right, and I'm going to stick with some pseudocode here. And you're going to love this or hate it. Possibly both. So here's a function called isBalanced. It takes a tree T and it gives you back a 1 or a 0. I'll do true, false, because it's pseudocode. So if T is null, return true. That's our first step. There you go. So if the tree is null, return true. That's just kind of a trivial case. Otherwise, what do we say? If the absolute value of the difference in the heights of the left and right subtrees is less than or equal to 1, and my isBalanced function applied to the left subtree says, yes, that's balanced, and isBalanced t right is true, then our tree is balanced. Otherwise, it's not. So this is like, a few lines of code. And we can actually write this in C and it will actually work. And there's no, overt moving through the tree and counting, depths and comparing your depth to the depth of the other node and finding the deepest node and all of that stuff. It's all kind of buried in here. But it actually works. And it's kind of miraculous. On the second statement, doesn't the first condition meet the requirement? No. All three of these are true. So you got to have all three of these things happening. And here's the reason for that. Right, there's a tree, the left and right subtrees both have a height of 5, but this tree is definitely not balanced. So it's got to be all three things. So yeah, see if the heights are close, see if the left tree is balanced, see if the right tree is balanced, and if so, then this tree is balanced. What's weird about this is that, you know, this is a algorithm for the isBalanced function, and the algorithm needs to use the isBalanced function. The reason this works, though, is because when we call isBalanced in here, we're calling it with a smaller tree. We're calling it with a left or right subtree of the original tree. And each time we call this isBalanced function, we're passing it a smaller tree, a tree with a lower height than the tree we were originally given. Which means eventually we'll end up calling this with a tree that has no height at all because it's null. And this base case will kick us out. Now if we don't have this base case, we segfault, because we just end up calling isBalanced again and again and again. And these parallel the two steps of a mathematical induction proof. Right? This is the base case, this is the inductive step. And if we wanted to prove that this gives us the correct balance for a tree, we can do that with mathematical induction. So what do? We make a proposition, P of n, that this algorithm works on a tree of height n. And we can show that if n is minus 1, this works because that's going to be this base case. And now you just need to show that if isBalanced works on a tree of height n, it works on a tree of height n plus 1. Well, if t has height n plus 1, then the left and right subtrees, you know, have height n, and so isBalanced will work correctly. So we can come at this from different directions. All right, so tomorrow is your exam. Monday is a holiday, so we don't have lecture again until Tuesday. But I wanted to get this out there to let you start thinking about it. Tuesday we will spin some code to deal with some of the stuff involving recursion, and we'll see how this actually plays out. And then we're going to just start going further and further into recursive algorithms. We'll redo the things we've done so far with trees recursively, and then we'll start developing new things from there. And this is, to me, where the course really gets fun, because it's going to, in a lot of ways, free us from thinking about a lot of minutia, and it's really kind of in the spirit of letting the computer do the work for us. So exam tomorrow, don't miss that. And I will see you in class, and then we'll continue this on Tuesday. All right, have a great afternoon. Thanks.